네.
그러면
약간 이런 게 좋은 게 그러니까 좋은
Hi,
것도
hello.
많고 막 하고 싶은 거
May I
많은데
have your attention? Hi, hi. Okay, now we're on time. We are already streaming right now. Well, welcome to the meetup from today. Actually, we have more people than before. That's great. A lot of people join for the lecture. Yes. So Kirb is gonna give us a lecture about like the 6 degree of freedom electromagnetic tracking he developed from scratch, which is absolutely incredible. Um, Without further ado, so I'm just gonna give the stage to Kirb, who is there. Yes.
Hello, so thank you all for coming. I am Kirb, and I'll be giving the lecture today, like Apto said, on the electromagnetic 6 degrees of freedom positioning system that I developed for virtual reality applications. So, bit of background about myself. I'm Kirb, 19, from Calgary, Alberta. I'm a recent graduate of a 2-year electronics technologist program, working as a technologist for a consumer electronics company. I have PCB and electrical design experience going back 3 years. This is the kind of thing I've been doing since like high school, both for hobby projects and academically or professionally. So some projects I've worked on include IoT devices, power inverters, switching supplies, a multi-channel EHD thruster driver, positioning systems, which is what I'll be talking to you about today. For some of my projects, I've done presentations for the Canadian Space Agency, Concordia University, University of Alberta, as well as my own college. This positioning system here, it was actually my capstone project for my final semester in my program. Just a blessing and a curse because the entire development was kind of condensed down to a single semester, 4 months. So, how many of you in the audience are currently using full body tracking right now? I see quite a bit of legs. Keep your hand up if that's a Slime VR or IMU based system. So, have you ever had the issue where after a while you just start getting yaw drift, or you have to continuously like calibrate so you're facing forward? And then for those of you using vives, I'm sure you've experienced occluding a tracker and then having it just fly out in the distance, and then you turn into a pretzel. So all current full body tracking systems can be classified into two major categories, which would be IMU systems or optical systems. So the IMU systems, this would include Slime VR, Herator X, or Mokopi. I'm not sure if anyone actually uses that for VR. But these are very compact, immune to occlusion, and they get great battery life because it's a very simple design. The issues come from yaw drift, as well as they require body calibration because the fact it's 4 kinematics SNO, the exact length of each one of your limbs to calculate the position. It's not a true 6 degrees of freedom system. It's 3 DOF that uses that 4 kinematics algorithm to get 6 degrees of freedom. On the other hand, we have optical systems, which would be Vive, Tundra, or SLAM in the case of the Vive Ultimate trackers, which these get you stable, true 6 degrees of freedom positioning. However, and you don't ever have to calibrate them as long as they stay still in your body. However, the issue is that you need a good optical environment for this. So if you have any like mirrors or excessive IR light sources or anything that would complicate that, you'll have issues with tracking. Their policies require lots of photodiodes and FPGA or cameras and a CPU for slime systems, as well as being very prone to occlusion, as mentioned earlier. So what if there could exist a tracking system that would combine the advantages of both of these, where you would have a tracker that's a full, stable 6 degrees of freedom positioning that can be fully occluded without losing tracking? Well, that is what I'll be talking to you guys about today. So I will be going over the basis of how magnetic position tracking works, existing systems that use this technology, and then going into my project, the magnetics design, the coil driver design, and the hardware of the tracker, as well as the full signal path and any conclusions that I got from the project. So let's start with the basis here. This graph here is a visualization of a ideal magnetic dipole, and for any position within here, there's a known vector. So if you have a device measuring the field intensity in the x and y axis in here, you could take the inverse tangent of that. That will get you an angle. The angle corresponds to the ratio of x to y position here. And then doing the hypotenuse of that gets you an absolute intensity. This intensity is equal to the inverse square of the distance from the center multiplied by a calibrated constant. And then there's the reference for this down there. One issue that you'd see if there's only one field source is that if you rotate the device, because you're only measuring x and y from a single source, if you rotate it, the perceived angle will be different. So it'll think it's in a position where it's not. One way of fixing this is if you have two dipoles, one on each axis. from this. If the sensor is able to differentiate which field is affecting it, then you can have both position and rotation. So this here would be a 4 degrees of freedom system, where the sensor would know anywhere it is both translationally and rotationally within here. And then I'm not making a graphic for this because it would be a complete mess. But for a 6 degrees of freedom position, if you imagine another field that was going out of the screen and back into it, that would get you 3 axes of position and rotation for a full 6 degrees of freedom position. There is a bit of an issue with this, where if the device is only measuring the magnetic field in X and Y, the measurement in one corner will appear identical to the measurement in another corner. So there's kind of a mirror position everywhere, where plus X plus Y plus Z is also valid for minus X minus Y minus Z. This is known as the hemispheric ambiguity. So to solve for this, one property must be known and common between the transmitter and the receiver. Some ways of doing this would be phase detection, since as you cross over the center, your phase would be 100. You would shift the phase by 180 degrees, so the signal would be inverted at one end. For this, you would need a reference signal on the device to compare phase against, which adds a bit of complexity. You can also use multiple transmit and receive coils. So if you'd imagine, you'd have one transmitter here, one transmitter here, and then the sensor is somewhere in the middle. Because it's receiving the signal from both of them, it would be able to validate that it's not in this mirror position here or this one, because it wouldn't be receiving the same signal from the other source with that. The way that I went about solving this was having an IMU inside the device, which always knows which way is down, and we assume that the transmitting coil is always in one orientation, because normally you don't want to move your base stations. Bad things can happen if you do that. So we always assume one way is down from the base station, and then we measure using the IMU which way is facing down, which would invalidate one of the possible positions. Some existing systems that have used this technology, one of the earliest ones is the Razer Hydra. This was introduced around the beginning of VR, so think like Oculus DK1 days, like very early before the Vive. These were a set of desktop VR controllers that were not wireless, they were wired. However, they used the magnetic tracking positioning system, which proved to be very effective for this. However, they were very limited in their range because it only has a 20 to 30 centimeter tether. So you can have like the base station on your desk, and then you can only move your controllers like that far. It's not really designed for room scale or full body tracking. These were quickly discontinued because the Vive wands and the Steam VR tracking system came out, and basically was better than this in every way, aside from the occlusion issue. A slightly more recent implementation of this is the Pico Neo 2, which what this headset did was it used typical SLAM tracking, like a Quest headset, where there's cameras on the headset that position the headset within the room. But if you notice, these controllers don't have any kind of tracking rings or cameras on them. The trackers position themselves in relation to the headset using electromagnetic positioning system. So the field source, it's kind of done in a backwards way to how these systems typically work, where the field source is in the controllers and then the sensor is in the headset. So kind of like switch between which controller is transmitting, and the headset is able to work out the position from the received field from that. There is a really neat video by Kai VR on this headset where he bought one and just used it for a while, and it was the only headset in existence that you can put your hands in your pockets and maintain controller tracking. This was very great. However, the rest of the headset kind of sucked and was very short-lived and discontinued quickly after the Quest 2 released. Finally, there's one currently in production system that uses electromagnetic position tracking. This is Amphitrack. They have actually released a demo on their YouTube channel where they've put one of their sensors on a headset and then put 4 field base stations in each corner of the room. And they're able to get HMD tracking, which is on the same level of precision as slime or laser tracking. This is also still in active development. However, the issue with this system is that it is very expensive for consumer VR. Their development kit, which just contains 3 trackers and 1 field source, runs 3,500 euros, which for that price, you could get a headset, a set of Vive trackers, and a computer. So I don't know of anyone that actually uses this for VR due to the price. So all the issues with the existing systems and lack of availability is what led me to creating my own full body tracking system using electromagnetics. Starting with the actual magnetic components themselves. So as I mentioned earlier, there are implementations of this already for those VR applications I mentioned, as well as some medical applications. These devices do exist. However, they are very niche. You can't just go on like Mouse or DigiKey and buy these. It's direct from manufacturer. If you're not buying like 500 of them, they will not even tell you the price. So I found these coils on AliExpress, which are very similar to the frame coils used in the AmfiTrack system. They're relatively cheap, and I believe these are replacement parts for Audi car keys, where they had kind of a system where if you hold the key near like one door, it'll only unlock that door, like near the trunk, it'll only open the trunk, because it can co-position itself with the car itself. But yeah, I was able to get a data sheet for these, footprint and everything, and they proved to be suitable for this application. As far as the base station magnets go, I wasn't able to find any available parts for this online other than like contact manufacturers who won't give you a quote unless you're buying like 500 of them. So I wound my own around a 3D printed base. This was just printed in PLA, and then I used 20 gauge copper wire or enamel coated copper wire to wind around it using a stepper motor to kind of speed up the process a bit. It was still quite a time-consuming process because you have to make sure that every winding is very tight on here and they're all wound in the correct order. One issue that came up with this was because it was printed in PLA, which has a relatively low glass transition temperature, as the coil heated up during use, it would slightly deform the plastic over time. So if you see in the image up there, that is when it was being wound. The windings are very nice and tight there, no gaps between them. However, after it's been extensively used here, you can see there's a lot of loose spots in the coils because it melted and kind of warped the coil base inwards a bit. To drive the coil, it is designed to be resonant at 20 kHz, 25 kHz, and 30 kHz. Each axis is running at a different frequency, so you're able to differentiate on the sensor from X, Y, and Z axis by pulling a bin out of the FFT for that frequency. So, as I mentioned earlier, where you need to differentiate between which dipole is affecting the measurement, you can do that through frequency separation. The inductance of the coils laid around ranges from 274 to 336 microhenries, which is a bit of variance. So the tuning capacitance had to be a bit variable to allow it to resonate at the correct frequencies. The range of this was about 80 to 100 nanofarads. And the ESR of the entire system was a bit higher than ideal at 1.2 ohms, which led to the coil heating issues that I mentioned earlier. The coil is also designed to be have an impedance close to 50 ohms at these frequencies, which made development a lot easier. So before this coil driver was developed, we were able to just hook the coil up to a 50 ohm output function generator and have minimal issues from impedance mismatch to drive it. This is what the actual circuit that is used for driving the coil looks like. It's a bit cursed, but it worked pretty well. So the way that this works is you have an H-bridge, and then inside of that H-bridge, you have the RLC circuit. So it will start with the H-bridge in one polarity. The current will begin flowing through the RLC, and as it oscillates, the current will eventually go negative through that. So when the current goes negative, there's a shunt resistor at the bottom that will measure the current off that, and then when there is a zero cross detected across that, it will flip the orientation of that H-bridge. So as the H-bridge switches, the current through the actual RLC itself is a very nice smooth sinusoid, and the current as seen from the supply is kind of a sine bouncing on that zero crossing, so we never have to generate a negative voltage or have a direct power amplifier connection to this. It is the current is controlled by the supply voltage, so as you vary what voltage is being supplied with, you can change the current, which is what we did for some closed loop current control, and the frequency is fixed, as I mentioned, set by a tuning capacitor. This is the actual PCB used for that coil driver. So there's 3 of those RLC circuits. Up at the top there, you can see the H-bridge with the supporting components. As I mentioned, the current through it is controlled by the supply voltage, so there's a variable buck converter on each axis. So in addition to the frequency counter and zero cross detection, there's also a peak detector, which will measure the peak current through that, and then we can do software to convert that to RMS and then run a closed loop algorithm. So if the current through the coil is higher than it needs to be, the supply voltage is decreased and vice versa. This is powered by USB PD 15 volt 3 amp. It's just a readily available way to get 15 volts, which is a suitable drive voltage for this. The kind of quirk you get with powering something over USB is that if you have a high capacitance system with lots of switching components and H-bridges here, you have a lot of capacitance there. And the USB spec does not allow for more than 10 microfarads, I believe, of capacitance on V-bus. So there's a FET that once power is negotiated, it will slowly turn the gate of that FET on to soft start all of those capacitors and not induce excessive inrush current. There's also a software override on here for starting and stopping. The oscillator is not actually able to self-start itself. So what has to be done is you manually switch the H bridge at approximately the right frequency a few times until the oscillation builds up, then it can switch to the free running mode. As far as stopping it goes, this turned out to be a way bigger issue than was actually expected. So when you have the drive current that I was running on here was about 500 milliamps RMS. If you have that current flowing and then you suddenly open all the FETs, that current will want to keep flowing somewhere, and usually does not find a very nice path to keep flowing. There's a lot of ICs that got damaged by them just being the path that the current took. A way to solve this is to just lock the H bridges in one position, so there's always a path for the current to keep flowing, which would be from ground to the supply rail. And because you're not actively switching and adding more current to it, the oscillations will eventually die out, and then it can be opened without damaging anything. The tuning of the coil driver was done using an array of capacitors on the back of it. So we're able to step response the coil and see the actual frequency of it there. If it's too high or too low, more or less capacitance can be added to these bus bars to tune it in to operate at the desired frequency. As I mentioned earlier, it uses USB PD as the power source, but that USB port is actually the only port on the device. So if we want to do like development or debugging on it, it has to be done through that port. And if you want to debug while it's powered, you'll need a way to get both USB PD power as well as data through the same port. So this is what led me to create this kind of abomination here, where you take data from one port, power from the other port, and combine into one Type-C port. Device looks like this. This is what happens when you make a silk screen in a Discord call. Moving on to the hardware design of the tracker. So what this must do is sample the signals from the magnetic sensor, perform both frequency domain and time domain analysis on the signal, then transmit that processed data to the computer. I'll go over the hardware design of this in 3 sections, being power, digital circuitry, and the analog front end. Starting with the power circuitry, there are 3 power rails in the device that must run from a lithium cell. So that'd be the low voltage analog front end supply, the microcontroller digital supply, and the low power always on supply. Because it's a lithium battery, it also must be charged. There's a 5-watt switch mode battery charger in here and a voltage based fuel gauge. I found an IC that was very suitable for this, the LTC3586. It's a monolithic PMIC that integrates a USB compliant power path regulator and charger. So if you plug this into a USB outlet that's only able to provide 500 milliamps, it'll only charge that. Or if it's able to provide an amp or 1.5 amps, it'll charge at the maximum it's able to there. The chip integrates 4 programmable switching regulators, only 2 of which I actually use. So that'd be one of them is for generating the 5-volt analog front-end supply voltage. One is for the 3.3-volt logic supply, so that'd be a boost and a buck boost. There are 2 other converters in it that are just unused as of now. It also integrates an LDO for the low power circuitry. The battery indication was done through a series of comparators here. Never do this. This wastes an enormous amount of PCB space, as well as you need to route like a million traces across to where all your LEDs are, when you could just like have an AEC on there and do it all in software. The device has a singular button on that's used to control both powering on, powering off, and the digital state of the device. There's a hard power off circuit implement in here, where if you hold the button for more than 15 seconds without any software involvement, it can fully cut power to it. The way that was achieved was whenever the button is pressed, you'll discharge this 10 microfarad capacitor through a 1 mega ohm resistor, which will eventually fall below the threshold of the Schmidt trigger and force every enable line to go low as a foolproof way of killing all the power. This ran from a 1.3 amp hour LiPo battery, which was able to grant about 4 to 6 hours of runtime. Some issues did pop up with the power supply in here, where when I was doing some testing of the noise floor of the device, just in an RF chamber isolated from all outside signals, where there's only one induced signal around 30 kilohertz, which is what the coil would be, there was always, no matter what the test setup was, a peak at roughly 4 kilohertz here. Tempo, a member of the DGen community, suggested this would be a beat frequency between multiple free-running switching inverters, which, after some EMC probing, turned out to be true. This PMIC here, all of these switching radars run at roughly 2.25 megahertz. However, each of them is running from its own oscillator. So there's a slight frequency shift between them just due to tolerance of the component, which is what created that beat frequency that popped up in the noise floor. Moving on to the analog front end, what this must do is amplify the very weak signals coming from the coil, the sensor, to a level that's readable by the ADC, while providing sufficient dynamic range not clip when it's close to transmitter. So the intensity of the signal on this coil follows the inverse square law. So if you're very close to the transmitter, you might see a signal of a few volts. However, if you're really far, it'll very quickly fall off to the microvolt range, inverse square law. So moving it away by a factor of 2 will decrease your signal by a factor of 4. Unwanted frequencies must also be heavily filtered out here, as the low frequency magnetic band, there's a lot of interference here. So anything like a switching power supply, any motor driven by PWM, or even speakers can produce noise in this frequency band, which can couple into here. So those frequencies must be filtered out. Another consideration with the analog front end is that it can't be overloaded when in the presence of a very strong field. So an example of this would be putting on top of like a transformer under a heavy load that would induce a very heavy 60 hertz signal, or putting it on top of a wireless charger that would also induce a huge voltage in the coil that shouldn't damage anything. For the design of the analog front end, each channel has its own dual op amp for mitigating the crosstalk. I could have went with a single op amp for all the channels to simplify the BOM cost. However, the issue with that is that, let's say this is a very on-axis, the measure coming from this coil is very on-axis, and the other coil is very off-axis. So you have a very, very weak signal here, very strong signal here. You don't want those to couple into each other and introduce position error. So each amplifier is fully separate. The passband of the filter is 15 kHz to 35 kHz, which gives a 5 kHz guard band on either side of the signal. This also makes sure that 60 Hz, which is absolutely everywhere, gets very well filtered out. Since, like, if it's anywhere near like a power line in your wall or transformer or anything, you don't want that to mess with your dynamic range. On the topic of strong signals coming in, there's a just very basic diode clipping network, which clamps the signal to the supply voltage of the amplifier to make sure that it doesn't damage anything. Since it is a single supply design, there's no negative voltage being generated here. Every virtual ground point and filter has to be biased to a reference voltage. There's a single reference voltage distributed across every amplifier of 2.5 volts. This is a 2-quadrant reference generated by an op amp. So if you have multiple filters sourcing current at the same time, it's the reference voltage generator is able to source all that, and if they're all syncing, it's also able to sync that without raising or lowering the voltage. As I mentioned, there's a lot of dynamic range needed for this. So like I said, like you'll have signals in the level of a few volts when you're very close, or microvolts when you're far away. There's a set of FETs here that will change the biasing, or change which resistor is effectively used in the feedback network of the amplifier to switch the gain digitally between 30 dB and 100 dB. Finally, the last stage of the pipeline is the digital circuitry, which this samples the signals that are coming out of the analog front end, perform the signal processing on this, and convert time domain into frequency domain, and then send this data over to the computer. This also, something that had to be done out of spite, was under voltage protection, because that really fancy PMIC that's designed to be used with lithium batteries I use, there's no under voltage feature on that. So usually with a lithium battery, you'd want to discharge it down to only about 3.2-ish volts. But this PMIC, if you give it 2 volts, the boost converters will just keep trying to go up to what it's supposed to output. So the under voltage had to be implemented in software to not over discharge the batteries. The main microcontroller used on the device was the ESP32S3. It's a very powerful 240 MHz dual-core microcontroller with an integrated 2.4 GHz radio. It's also quite the power hog. This thing is the sole reason why this isn't able to get like 10 plus hours of battery life. This alone, while running all the digital signal processing and transmitting the data wirelessly, uses 200 to 300 milliamps, which is quite significant. The ADCs used were there's two 24-bit 96 kill sample per second ADCs. Each one's dual channels, so there's a total of 4 channels. So 3 of those channels are used for the X, Y, and Z axes respectively, and then the last channel is used for for measuring the reference voltage. The reason why the reference voltage is measured is there's still a small amount of noise on there. So you'll get like a couple microvolts of noise if you have like multiple filters syncing into it at the same time, which will slightly raise that voltage up. So if we measure the voltage on that the voltage of that reference, then invert that signal and add it to all the other ones, we're able to cancel out any combo noise that would exist between all 3 channels. There's also the IMU used for the mentioned earlier hemispherical ambiguity. It's a BMI 270, just a kind of basic Bosch IMU. All that it's really doing here is measuring which way is down. However, through further software development, there is a capability of sensor fusion and interpolation for this. So you could reduce any jitter by kind of doing sensor fusion with the IMU, and also fall back to purely integration of acceleration when the signal drops. It would also be possible to run like a Slime VR-like algorithm when the signal drops out with these. The PCB used for the tracker was a fairly standard 4-layer board, stack up signal, power, ground, signal. It's actually impossible to make one of these without using 4 layers, at least using a coil like the one I used here, because if you look at the pin mapping here, the x-axis coil starts here and terminates here, y-axis starts here and terminates here, z-axis starts here and terminates here. So you have 3 crossovers here that all have to be on different layers because you're running the signals differentially. So like you'd have the differential pairs, one here on different layers of the board, so that they don't ever interact and they're as close to each other as possible. Once that gets down to the input of the analog front end, it converts it from a differential signal to a single-ended signal, as the entire analog front end is a single-ended design. The coil, you also mentioned, there is very minimal copper solder mask or anything around that. That's because, once again, to the inverse square law, if you have any metal that's nearby the sensor, you'll have field distortion around it, which causes positioning error that can be calibrated out. However, attenuation will push your signal closer down to the noise floor and reduce performance overall. Another board that was implemented in here, which wasn't really necessary, was this flexible printed circuit that integrated 32 addressable LEDs. This was used for like power state indication, as well as kind of a demo that I was planning on doing where it would always have a compass on it that points towards the base station. It's kind of like a very easy to demonstrate way that it's functioning. This WS2012s get very bright at full duty cycle. So I actually, for all indication purposes, I ran them at like 3 or 4% duty cycle. When it's at 100 showing white, the thing turns into a quite bright flashlight that lights an entire room while drawing an amp from the battery. This housing is not actually supposed to be transparent. It just looks that way because of the amount of light shining through the thing. The housing of it is a 4-piece 3D print. Fairly simply, you just have main housing, button, the cover for the FPC, and a snap fit lid. I went with Slime VR style straps that kind of mount out the side like this. The reason behind going with a Slime VR style mount instead of the standard Vive mount is the Vive mount, you'll have like a tripod screw that goes into the device, and then that goes onto a strap. However, the strap, you don't know how much metal is used in the construction of that. So it could be just like a small screw underneath the tracker, and that's all the metal there is, or it could be like a full metal base plate, which would go under the coil and shunt the fields from there. So to eliminate any error you might get from a strap that contains a lot of metal, is just using these loop points for Velcro straps to attach to. So in total, the full signal path of a device like this would start with one closed loop for driving the coils. So you'd have your variable power supply running to the zero current switching driver, resonant tank, and the coil that generates the field. The current through these coils is measured, goes through the first closed loop back to the power supply. So this loop here, the goal of that is to maintain the transmit power at a constant current. From the generating magnetic field, there's the free space and off-axis attenuation, and then we get picked up by the pickup coil sensor on the tracker. This goes into the second closed loop, which is the variable gain analog front end, which gets sampled by the ADC, and then we run digital signal processing. Time domain digital signal processing runs back to the gain switching logic. So if you have a certain amount of signals that are above a threshold, or if you're clipping at the top of it, you'll switch from the high gain range to the low gain range. And then if you're at the low gain range and then no signals fall above threshold, you switch to the high gain range to maintain the maximum dynamic range of the system. The other output from the digital signal processing is the frequency domain data. This is done through a fast Fourier transform algorithm, and then we isolate the frequencies from it. So the 20, 25, and 30 kilohertz from the field generator, those get isolated to just single FFT bins, which are sent over a wireless link to the computer, which runs the positioning algorithm and the visualizer. Over on this side here, I have some of the actual output data from the device. So this is kind of a graph over time of what the signal looks like. So each row here is the axis from the transmitting coil. So transmitting coil x-axis, transmitting coil y-axis, transmitting coil z-axis. And then each row is the receiving coil. So you have a 3x3 matrix that you pass through to the positioning algorithm. This is a full visualization of a bit more data where we have the raw fast Fourier transform output of the device, this time domain data, and then the 3D visualization of the position of the device. So in the end, I was able to produce 5 trackers and 1 base station. The functioning prototype I made has a detection range of roughly 2 meters before the signal falls below the noise floor. The tracking jitter was not great, once again, to do noise floor issues. So at a distance of 30 centimeters from the transmitter, you get about 10 centimeters of position jitter. And like I mentioned, battery life is 4 to 6 hours. So with this prototype here, I was able to demonstrate that the viability of a low-cost magnetic tracking system for VR is possible. However, the current state of this prototype, due to the noise floor issues, is not usable for VR. So there's some room for improvement with the design, such as filtering and more advanced sensor fusion algorithms, actually incorporating the IMU into the positioning solving stack, further tuning of the analog front end, and power line filtering. The 5-volt analog supply range, while it is low noise, there's currently no filtering on that. So you get a bit of noise from your switching power supply coupling into the output signal. Power efficiency could also use a lot of improvement. Right now, the transmitting coil, while active, draws about 40 watts, and then the receiving device draws about 300 milliamps from the battery, so you're able to get 4 to 6 hours. However, if this switched from the ESP32 platform to NRF, that could drastically improve the battery life, as well as directly deriving the coil from a power amplifier instead of an RLC circuit. The thing with the RLC circuit is it's very simple to kind of build and design it to operate this way. However, as the coil heats up, the inductance will slightly change. Same with the capacitors. You've got a temperature coefficient on everything. So as it warms up, your frequency might shift from like 20.5 kilohertz to like 20.4, 20.3. It'll just slowly shift around over time, which means you'll have to actively correct for that on the tracker to know which FFT bins to pull out. And this also would make a heterodyne or lock-in amplification system impossible, as you would have to constantly be synchronizing the phase and frequency. Where if you were driving it directly from a power amplifier that's able to just do a fixed frequency, fixed amplitude, you can have a almost exact reference signal on the device to compare against. What do I want the future of this project to look like? I'm currently in the progress of a full system redesign. Within the DGen Tech community, a lot of ideas have been suggested, such as using a lock-in amplifier or heterodyne architecture, where this would, instead of just using FFT to pull out the frequency domain data, you have a reference oscillator, either in analog or in digital on the device, which gets mixed with the incoming signal, pull out the signal, a single frequency content, which could, in the case of a lock-in amplifier, be below the noise floor, which would improve the tracking performance. There's also been suggestions for more signal processing and filtering, utilizing multiple sensors, or further developing the algorithms. So I would like to end this off on a note saying that if anyone has any interest in the project or ideas for how they can improve it, or just want to see it develop, don't hesitate to head over to the DGen Tech Discord. Invite is there. and I'd love to see some feedback about the design or anything that could be improved. Thank you all for coming to my lecture, and now it's time for questions.
Clap, 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 clap.
Kirb, thanks for the lecture. I think you mentioned that you use IMU with magnetics. Does the magnetics affect the IMU?
So this IMU, it's only a 3 DOF IMU. It doesn't incorporate a magnetometer. So there shouldn't be like magnetic interference with this, but I'm actually not sure if magnetics can affect typical IMUs. Because I guess like the internal forks in there could be slightly pulled by a field. But the fields generated from here, I don't think would be strong enough to actually meaningfully affect the measurement of an IMU without a built-in magnetometer.
Take a question from YouTube. It's asking, why would you choose to use an RLC circuit compared to crystal oscillator? Or did I miss something?
So the reason behind using an RLC is because the RLC is also, in a way, the power amplifier, where it's directly driving the coil at 500 milliamps RMS. A crystal oscillator, you're not able to draw anywhere near that much current from it. So that's why the RLC is used. It's both the oscillator and the power amplifier. Salix?
Yeah. So you say that the frequency drifts over time from the transmitter base station, and so you have to change which.
Bro, everyone crashes. Exactly around time. It just happens.
Well, intermission here. That I'm like kind of busy like managing all these things, but you bring up the no-load trackers, right?
Yeah.
Oh, man.
The what trackers?
No-load trackers. Those are like the like controllers that use like magnetic tracking, like funny balls on them, right?
So those be like the PS Move controllers?
No, it was like one of those like weird heads. It's like a I don't know what we put it for or whatever.
Oh, the Pico?
The Pico 2.
Yeah, I think it used them, right?
Yes.
Yeah, those are the no-load trackers to my knowledge. The fun fact that I know about those is that Nolo means embarrassing in Finnish, which is kinda appropriate.
It's funny.
So, Kirb, I have some question.
About the base station.
Yeah.
So
Go ahead.
You said I'm really curious about the controlling system. I mean you control the current by controlling the voltage you apply to them, and you said you use the buck converters. So how do you control
Yes.
them? You control them by changing the setting voltage by the buck converters, or like using the DAC on the ESP32 on there, or how can you control
So
the voltage there?
the way that this was done was each of these modules here has both the switcher itself as well as a digipot. The digipot is within the feedback network. Yeah, so the digipot, you change the set point of that, which will affect the output voltage as in the feedback loop of the buck converter.
So digipot itself, so is it controlled with ISQRC or like SPI or something?
They're controlled over an SPI bus from the ESP32.
Yeah. Oh.
And we just have an ADC of the ESP measuring that output of the peak detector to run the software closed loop.
Oh, yeah. Thank you for explaining. I was curious about that. Yeah. I mean, I use some buck converters, but they are really cumbersome to change that. So change the voltage, bit of voltage. I mean, yeah. So yeah. Thank you.
Thank you. Looks
Okay,
like
Salix is back. Hi, Salix.
My home Wi-Fi, my router just rebooted itself for no reason, so that's fun. Anyway, too much magnetic field, I guess. Anyways, so you said that you have to change which FFT bin you're sampling from.
Yes.
In order to do that, do you just like do you just have you select like the peak within some given range, or how do you choose that?
So it's directly choosing one of the bins to pull from. So the FFT, where it's being ran on samples of 1024 time domain signals. So you get 1024 frequency domain signals. So you just round to the nearest bin that would contain that frequency and then pull the amplitude from there.
Oh, right. Because is it like your base station is telling you the correct frequency to sample?
Yes. There's a frequency counter running on it's able to transmit to the tracker which frequency is being transmitted at.
Okay. Cool.
So we got a message on YouTube. Hi, Mr. Kirb. I always been a big fan of your work. I don't know if someone knows you.
What's their name?
Distro Karim.
Oh, I know him. Hello, Distro.
Cool.
Yeah, it was on quite a compressed development timeline where it was just limited to one semester, 4 months for the whole thing.
Do you have ADHD?
Not diagnosed, but probably.
Oh, I was wondering, like, was this like a midfield bender? Because that's like perfect for like a midfield bender. ADD medication power is keeping me up still after the. I haven't slept since the previous presentation. Anyways, more questions.
So, Kirb,
I have one.
Oh, sorry. Yeah.
Go for it, though.
Tempo?
Yeah, go first.
Right.
Sure. You have decided to make the stack up signal, power, ground signal, right?
Yes.
What is the ground? What is the power plane reference to? Which power plane is it? Is it the analog power plane, or which power plane is the polygon?
So for each individual voltage rail, there is a separate power plane. So it might be a little hard to see here, but coming from the PMIC in each switching converter, there is the USB V bus, which is this area here. Output to the actual battery is this plane here. Then we have the 3.3 volt pour coming here. Or no, that's the 5 volt pour, and then 3.3 volts goes underneath and back up to the USB here. So each kind of section has its own individual power plane and path going to the PMIC.
Okay, I see that. I would have a suggestion to next time put a ground to the top, because you really need to have a reference point. All those signals are going to be referencing the power plane below it, and that might get you a few points from your signal to noise ratio. But other than that, it's an impressive project.
I guess I would, yeah, because you have these are the amplifiers themselves. So I guess you'd have like different power rails running underneath them that could cause a bit of coupling there.
Yep.
Okay, any more questions? I'm here.
Flannan?
Oh yeah. So sorry, I'm asking so much, but I'm really curious.
No, it's
For me, are developing implement. So I believe the USB32 supports like Arduino, such thing kind of environment. So what program or development environment do you use? Like platform IO or? I mean,
For this, I was
like.
Yeah, I was directly using the ESP IDF IDE, which is a huge pain in the ass. But yeah, it gives you the lowest level access to the hardware functions of the device to use IDF.
Oh, thank you. Good to know.
Sinher?
Got another from YouTube. Book asks, was any signal processing such as FFT performed on the micro or on the PC?
It is performed on the micro. The ESP32 integrates some hardware signal processing capabilities within it with vector instructions, as well as the ESP DSP library makes it simple to make use of these. So the FFT can be run in real time on the microcontroller itself. Felix?
So, way at the beginning you said you can determine angle and position using basically magnitude and of that. So currently, do you just like you take your FFT and then whatever value that spits out, you use that, or is there like incorporation of like do you do like a rolling filter where you kind of use previous states to estimate next state?
So currently it's a purely linear system where there are these 9 amplitudes that you're pulling out. So transmitter X affecting receiver X, transmitting X affecting receiver Y, and then transmitting Y affecting all of those. So you have 9 elements. It's a purely linear system. So the input directly goes through a linear system to the output. There's no like filtering or averaging currently involved in the positioning algorithm.
Are you familiar with the Kalman filter?
Yes, Kalman filtering I am familiar with, however, it's not been implemented yet into here.
All right. Any other questions? Dia, hi Dia.
Have you considered transmitting
What's that?
a code stream instead of a pure tone to gain some
The
noise rejection?
So the issue with modulating the carrier signal that's being sent out for positioning is because there's a frequency response to everything. If you do like a frequency shift keying on there, you'll have like a different amplitude, even though the position is the same, very slightly. As well as transmitting information over this isn't really all that necessary, I believe, because of the fact that there's a 2.4 gigahertz rate on each device, which is able to do Bluetooth or Wi-Fi communication to each device without needing to modulate the magnetic field.
All right. We have another question from the YouTube, and you can.
We could ask how much more time do you think you'd have to put in before it would be viable for VR use?
So with the development they did within the 4-month period, I honestly feel like there's another year of development that could go into all the aspects of this, because this was quite a rushed project here. That if there's a full like redesign of it through multiple iterations, I feel there's another year-ish of development that could go into this.
Another on YouTube, Mithink asks, you mentioned the power of the transmitter is actively controlled. How much does it vary?
So the target current through the coil is 500 milliamps RMS. The driver is able to go up to 1.6 amps RMS before it starts causing issues. However, that makes things get very hot, and you also can't directly run from USB PD because it draws about 80 watts while doing that. So 500 milliamps per axis is the target that's running at.
All right.
Salix?
What software do you use for data visualization?
This was just hold on. For that, I was using Python and Matplotlib primarily for it. So it's very slow and hogs all the CPU to run all these Python visualizations, but it was something simple that was able to be done quickly.
Yeah, that sounds about
That's
right.
all that matters.
Yeah. Yeah, the way that the local visualizations were done, there was, I think, like 4 or 5 different Python scripts that had to be started in like a specific order, where one like grabs the data from the transmitter to determine the FFT bins, one grabs the data from the device, one runs the visualizations, one does the positioning algorithm. It was a mess that used like 60% of the CPU on my laptop to run it.
But that sounds like a wonderful Python arrangement. It's perfectly normal.
All right.
I'll take one question if I can. How did you come around choosing the ADC? what was like your mental process to get to the ADC that you've chosen? Because you have some audio codec one, right?
Yeah, so it's using a PCM audio codec. Kind of the reason behind going behind that was the frequencies that are being ran with here are very close to audio frequencies, where the highest one is 30 kilohertz, and audio ADCs with decent bit depths and sample rates are fairly cheap to get, and it worked out for this application. It is a 24-bit ADC, however, the effective number of bits in ideal conditions ADC is realistically around 18 bits. But yeah, it is kind of limited where in each second of sampling, you're only getting 3 cycles, or yeah, you're only very slightly above Nyquist of that 30 kilohertz sample. So you're only getting 3 samples per waveform there. So the ADC is just chosen as something readily available and fairly low cost.
Yeah. One thing that I thought about, I haven't really dug too much into the datasheet, but sometimes these specific audio codec ADCs have low pass filters to keep inaudible frequencies out. You might be hitting something there.
Yes, so this has a anti-aliasing filter that is set at 48 kilohertz in there, which is the Nyquist rate of the ADC. So it's not one that filters it out just beyond 20 kilohertz. It doesn't begin filtering until 48.
But it's good that you've taken that into account, right? Yeah.
All right.
Is that all the questions?
Any other questions? Or we can just wrap it up. Yeah, Heisner.
Sure.
Questions from YouTube. From Mitsink, how much does it hover around that target? If I understand variation could cause drift. I'm guessing this is regarding the previous question that Mitsink asked about the active control of like transmitter power.
I don't actually have a discrete measurement on how much that varies. However, once it gets up to temperature, the thing that would cause the current to vary would be like temperature coefficients of the RDS on the FETs or the ESR of the coil, the capacitors. Those are what would lead to the drift of that, but once it's at steady state as per temperature, it shouldn't drift very much. But I do not have a particular number on that.
And then there's another one. Chris asks, you said that you were controlling the current by using peak detection circuit. Would there be any advantage of switching to a low pass filter or average current measurement?
The thing with this design is that because it's a sinusoid, if you average that current out, it would average to 0. So you'd have to measure the amplitude of the signal, and the easiest way of doing that was just a peak detector. That the way it worked was the output of the amplifier for the shunt would go kind of through a op-amp arrangement that would act as a peak detector, where you'd have a diode in the feedback loop, and then a capacitor. So the highest point in that signal is what's sampled, and then a kind of low pass on the output of that.
Okay. Anyone else has any questions? Or we can just wrap it up here. I mean, we had a good amount of questions, I think. Okay, let me just over here. Okay, and we can just wrap it up now. The lecture. Thanks everyone for joining. Like, to be honest, this was like amazing. I love this work. I'm really excited, actually, personally, to actually see how this develops. We should actually follow this up. If anyone has any questions, suggestions for how to follow this project or anything, just join the DigenTech Discord server. The link is here. Kirb is gonna post any update he's gonna make on this. Also, any questions you want to make him also as well, Discord server, or you can leave a comment on the YouTube. This stream, we're gonna wrap it up now. This is, of course, as always, we are gonna upload this as a video on the YouTube channel in like 3 weeks or so after we edit it. And I don't know. Thank you all for coming. This concludes like the formal part of the meetup, but please stay, just chat with each other. We can drop a more chill instance if you guys want. All right. Thank you.